Hello, in this demo we're going to look at how we can enhance Neutron security using APIC L47 service insertion. The idea is to enhance an OpenStack cloud experience with enterprise security. We will be looking at a very simple lab where we have deployed an OpenStack cloud where the SDN component is provided by the APIC Opflex plugin integration using ML2 mode. This cloud will have connection to the external internet using L3 out interfaces. Let's look at how this looks like in APIC. In APIC, the OpenStack Opflex integration is accomplished by leveraging or implementing a VMM domain, a virtual machine manager domain. In a VMM domain, we can have multiple OpenStack clouds. In this case, we have one deployed with Liberty and one deployed with Mitaka, GBP and ML2 respectively. We can see the VMM integration by looking at the OpenStack controller, and this allows us to see a list of the hypervisors, the virtual switch implemented with OpenVSwitch controlled by the APIC, and we can see for each of the hypervisors the virtual machines that are running on each of them, the IP addresses, MAC addresses, as well as the specific network core that they're running on the virtual switch. In addition, OpenStack projects will represent tenants in ACI. For instance, here we're going to log into our OpenStack cloud powered by APIC, and we can see that we are in a project called New Web Apps. That project will have a corresponding tenant. And within that tenant are the ML2 New Web Apps. Here, for instance, we can see that the Neutron administrator has created a router with external connectivity and two different networks, My Web App and MyDMZ. And those are exactly what we see here, My Web App and MyDMZ, with the corresponding application profiles and EPGs for representing those networks. This enables the Fabric administrator to have the same level of visibility for OpenStack networks and users as they do for anything else in the Fabric, and to leverage things like the health scores for monitoring, so we can quickly see, for instance, the health of the tenants of the specific OpenStack projects. Now, in this model, we provide distributed routing. The routing is performed both at the hypervisor and in the Fabric. The default gateway is distributed to the OpenVSwitch and to the leaf switches in the ACI Fabric. Security is defined by the security groups that are defined, Neutron security groups defined by the project administrator and enforced at the hypervisor. This enables for optimal east-west traffic to flow between the different entities. We can take a look at that as well by looking at Web Server 1 and Web Server 2 that will be on the 10.100.114 subnet, 14 and 15 being the IP address of the servers. We can look at this here. This is the My Web App where we have Web Server 1 and Web Server 2. We can open a console to Web Server 1. And we can look at the IP address that has been given, 10.100.114. This is also visible to the Fabric administrator. Under the tenant for that particular project, we can see the EPG, and within that EPG we can see the endpoints connected. We see Web Server 1 and Web Server 2, and we will be able to ping from Web Server 1 to Web Server 2. In this case, they are on different hosts, CentOS 1 versus CentOS 2 hypervisor, so that traffic is being routed in the Fabric and going through the Fabric. Security is defined by the tenant administrator, as is the case in OpenStack, by deploying security groups or configuring security groups. So through the use of security groups, you can define whether servers can ping to one another and whether they can have or not access to the public internet. These security groups are implemented in distributed way by the Opflex agent programming them into the hypervisor, the KVM hypervisor. How do we handle external connectivity? What happens if these instances want to connect to external source, to external traffic? For this, we will leverage two concepts. We will leverage the L3 out interfaces that will enable you to connect the tenants through the common tenant to a shared L3 out that connects to an external router. And we will leverage source NAT that will be distributed to the hypervisors. Each hypervisor will be assigned an IP address that will be used to NAT the traffic of many instances, of all the instances running on a particular hypervisor, towards that external router. The security is still provided by using security groups defined by the OpenStack project administrator. Once again, if we look at this, we can see once again that our topology includes an external router and external connectivity. But since our servers are receiving private addresses, we're using source NAT. Source NAT is effectively functioning, and we can see that we can ping IP addresses that are external to our fabric, like for instance our proxy server. That's on subnet 507. That traffic is going to appear on the common tenant. On the common tenant, we will have a dedicated application profile for that OpenStack project, where we can have one or more EPGs dedicated to multiple projects or to a single project. In that EPG, we will see the IP addresses dedicated for SNAT, like in this case 172.16.10.2 and 172.16.10.3 for each of our hosts, CentOS 1 and CentOS 2. These subnets are going to be appearing as well in the bridge domains that Neutron automatically helps define here. And through that bridge domain, they are advertised to our external routers. So we have an external L3 out on which we can use dynamic routing. In this case, we are configuring OSPF. We have a full adjacency, and we can look at the routes. So we can see that we do have a route for the 507 subnet towards our L3 out interface. We also have a subnet for the 192.168.180 and the 192.168.200 that we will use later in our demo. The connectivity is provided between this application profile and the L3 out by means of the external EPG internet access that helps define every traffic that needs to leave the OpenStack cloud, and a contract, and this contract essentially is a permit any that enables access between the source NAT addresses of each of the hypervisors and our external L3 out. Again, NAT is performed at the hypervisor level, and security is enforced through security groups. But how can security teams impose control on external services? How can they be sure that users can access only specific services and not others? The security administrators can override the security groups that have been defined by the tenant administrator. But we can attach a service graph to the contract that redirects traffic towards the L3 out, that allows traffic towards the L3 out. And by doing this, we can redirect traffic to any next generation firewall. This could be literally any next generation firewall. In our example, we will be using a Cisco ASAV. So once again, we're looking at our web server 1. We can see it has IP address 10.100.114, and in this case we're going to ping an external IP address leveraging again the SNAT functionality. We're going to ping to a server that is outside of the fabric, this server here. It has IP address 192.168.200.1. That's the one we're pinging to. That ping is again leveraging the L3 out and the SNAT as we've said before. And what we're going to do now is we're going to identify our contract here. This is the contract we're going to be working with. Currently it has no service graph attached. We already have a service graph template that we have deployed. This service graph template will enable us to pick on a particular firewall, in this case a virtual ASA, between two EPGs. So let's assign that one to the subject of our contract. We can select a service graph. Currently we have this one, ASA RDO NG firewall. As we do that, the APIC will configure this firewall, ASABL302, with the required policies per the function profile that we've previously defined, where the security admin has decided the type of access that will be allowed for cloud users. Here we can see the configuration is happening. We refresh. We can see the interfaces are being configured now to insert the firewall. And we can see that now we've built an inbound rule that allows traffic from 192.168.201 to 172.16.2. So this is the entry that allows the traffic, the ping, to respond, to come back from our external server towards our source NAT IP address and into the cloud. How is this happening? This is happening because the configuration will have objects that have been defined for our representing traffic. So in this case, we have only two rules that were defined by the security admin that allow traffic into the cloud. We only allow ICMP and we only allow HTTP. So regardless of what the security group that the project administrator may have configured, even if it's a permit any, now only these two protocols will be allowed from external sources towards our cloud instances. The APIC automatically has learned the IP addresses that it needs to configure for each of these objects. For instance, the external interface is represented with an any because it's our default, whereas the internal one is represented only with the IP addresses of our SNAT configuration. Our ping is still successful, but now is going through the firewall and logged on the firewall. As we can see here once again. We stop the ping, we can turn down the connection, and as we start the ping, we will build a new inbound connection. But now, how do I add a floating IP? Floating IP is a concept in Neutron that enables you to assign a public routable IP address to a specific instance. Once again, we implement floating IP in a distributed way, and we perform the NAT between the floating IP and the instance at the hypervisor level. What we're going to do is we're going to leverage the endpoint attached notification of a managed service graph. Whereas the SNAT configuration that I mentioned before could have been handled with an unmanaged service graph, it's better to use a managed service graph to leverage endpoint attached notification. So we will look at our two servers, and we will assign floating IP to those two servers. This will allow the APIC to learn those IP addresses in the common tenant and automatically notify the firewall that those IP addresses are to be allowed. This means that the cloud user experience is maintained, is preserved. We don't need the cloud users to open tickets to security team to enable floating IPs to be allowed. But those floating IPs will only be able to expose services that the security administrator of the firewall has previously defined. For this, what we're going to do now is we're going to go back to our OpenStack configuration. In OpenStack, we can see these instances. Here they are. And what we're going to do now is we're going to assign first to web server 2. We're going to assign a floating IP. It's going to be floating IP 172.16.20.6. So let's go to our external server and already start a ping to that IP address. Right now, nobody's responding to that ping. But as I associate that IP address, again using standard Neutron configurations, the following will happen. That IP address will be learned now by APIC. APIC now knows that our web server 2 is also running with 172.16.20.6. APIC will now notify our firewall. And the firewall now has added the 172.16.20.6 because APIC informed that this is a valid IP address. And as a consequence, our ping will be successful if only we use the right IP address. Okay, 172.16.20.6. That is successful. Let's repeat that since we made a big mistake. .7 now. So let's assign .7 to this other web server 1. So once again, web server 1 will be learned. We're in the process of learning it. So these instances will now communicate to one another using their private IP addresses. When web server 1 communicates to web server 2, it will do so inside internal to the tenant. And that traffic will be routed either locally or internal to the fabric between private IP addresses. However, when they communicate to external IP addresses, they will be routing through the common tenant. Once again, our firewall will have learned the new IP address. New IP address is learned, and our ping is successful. So we have seen that we can add security defined by the firewall administrator. Firewall administrator can use their tools to define whether new or less services are allowed. We can add rules here, we can delete rules here by using objects that will help us dynamically learn the IP addresses that have been used or assigned to the cloud projects. And this can of course be used also with full stacks launched, for instance, through HIT. Let's take a look at that as well. So we have this quick HIT template that will do a few things. It will create a new instance for WordPress. It will create a new network in Neutron, and this new network will assign a subnet to it. We will create a MySQL instance, assign it in that network. We will create a security group that will only allow the WordPress instance to communicate to the MySQL instance, and we will assign an IP address, a public IP address to the WordPress instance. So let's do that. Hit stack create my WordPress -f. There we go, it's done. So what is going to happen now is HIT is the orchestration engine of OpenStack, and HIT is working. So it will slowly be performing functions, right? For instance, it's already created the network and the subnet. And after a while, our stack has been completed. And we can see that a new network has been created. MySQLnet with its own subnet. And a matching configuration is to be found here, MySQL subnet. In MySQL subnet, we can find the SQL database that was created by and in the My Web App is where my little HIT template connected our WordPress. So the communication between our WordPress running on CentOS 2 and our SQL server running on CentOS 1 will be east-west, will be filtered by security groups defined by the heat template, and will be using private addresses. But our instance here is also accessible through the web because it's a WordPress. So our WordPress server has also been assigned a floating IP 2014, and we can see that as well. Here's our WordPress 2014, and as a consequence of that, our firewall also has added 2014 to the list of IP addresses that are granted services. In this particular case, we allow ICMP and HTTP. That means now I should be able to ping 172. Indeed, I can ping it, and I should be able to open a web browser and see my new ready to install WordPress. We can quickly see the firewall logs. Let's match on the IP address that we have it. The WordPress is available, and indeed if we match on the source IP address of our desktop, we can see that the firewall is logging those TCP connections to port 80 to reach our WordPress server. Thank you for watching.